Welcome to capacitor charge and discharge. Before we analyse the rates of charging and discharging, we're just going to review some of the variables that impact these rates. We're going to review some animations, specifically an animation that shows this relationship. We're going to look at the function of the dielectric. We're going to have a look at capacitors in circuits and how the charge moves around. And then finally, we're going to have a look at an animation of a charging capacitor. In this animation, we can see how the capacitance is affected by the separation distance and the plate area. As the separation distance decreases, the capacitance increases, and as the plate area increases, so does the capacitance. This animation is to demonstrate the presence of a dielectric and its effect on the capacitance of a capacitor. Currently, the capacitor has a low capacitance, and if we put the dielectric in place, the capacitance rises. If we charge the plate and have a look at the electric field and the behaviour of these polar molecules, then we will see why this happens. So here the plate is charged with no dielectric. You can see how the charges are equally spread across the surface of the plates. And we can also see that there is a voltage between the top and the bottom plate. When the dielectric is placed in, that voltage decreases. And the reason for this is because the electric field is now smaller. The distance has remained the same, so the voltage needed to go down. The reason why the electric field has decreased with the dielectric is due to these polar molecules. Look very carefully, you can see the positive is aligned near the negative plate and the negative charge is aligned near the positive plate. When the dielectric is out of the electric field, the polar molecules are arranged randomly, they are not aligned, and when it's in the electric field, they are aligned. Notice that the positive to negative direction is upwards, where the electric field between the plates is downwards. So what's happening here is that the electric field within the dielectric is cancelling some of the electric field between the plates, reducing the total electric field, reducing the voltage, and therefore the capacitance goes up. Here we can see three capacitors in series with each other. The first capacitor has a very large capacitance, the second has a middle capacitance, and the third has a very low capacitance. As we charge the capacitors, we will see the behaviour of the charges in the circuit. With a small voltage, you can see that each of the capacitors has charged slightly. As we increase that, we start to see the pattern whereby the capacitors are charging evenly. Even though this capacitor at the top is capable of holding more charge than the others, it does not. If we maximise it, we can see that they have equal charge on them. This is because the electrons coming from the negative terminal of the cell travel to this plate. They repel the same number of electrons on this positive plate, which travel to the next capacitor, which again repel the same number from this plate and travel to the next capacitor plate, and again. So this capacitor at the top is not capable of getting any more charges on it than the smallest capacitor in the circuit. If we have a look at the voltages on the low capacitance plate, that is 0.8 volts approximately. We have a look at the next one, that is even smaller, and the smallest voltage is on the highest capacitance capacitor. And you'll notice if you rewind and add these numbers together that they add up to equal the voltage of the power supply. Capacitors in series behave very similarly to resistors in parallel. If we have a look at capacitors in parallel, we will see that they all act independently of each other. So as we increase the voltage supply, we see that the large capacitance capacitor contains the largest charge, the middle contains the middle charge, and the smallest capacitance capacitor has the smallest amount of charge on it. They're all working independently here, and that's because they all have independent connections to the cell. If we turn it right up, we can see that this relationship stays the same. If we look at the voltages, we see that this is equal to the cell, as is this one, and as is that. In this simulation, we can see a capacitor connected to a cell with a resistor in series. We can see the capacitance. The circuit is open and the capacitor is discharged, so there is no energy stored. The circuit is open, so there is no current flowing. And because the capacitor is discharged, there is no voltage across it. This is the voltage of the capacitor. We can change the distance between the plates and the area of the plates. And as it's set up here with the largest area and the smallest distance, this capacitance is at its maximum for this simulation. I'm about to do a quick demonstration to show how the time to half changes with resistance and capacitance. So what we're going to do is we're going to close the switch and charge the capacitor. Initially, the current will be high and then will go low. What I'd like you to do is get a timer and time how long it takes for the current to halve from its maximum value to half that value. Pause the video to get yourself a timer, please. So with maximum capacitance and resistance set to a middle value, I'm going to close the switch and see what the maximum current will be. Then we'll turn the animation on and let it run. So there is our initial value. It's going to be 1 amp. I will give you a countdown to start the timer. Stop your timer at 0.5 amps. 3, 2, 1, now. Okay, you should have a bit of data. What I'd like you to do, please, is rewind and replay that and take a mean from at least 3 data points. I'm now going to change the capacitance so that the distance is at a maximum and the area is at a minimum, making the capacitance a lot smaller than it was previously. And we're going to repeat the experiment and see which one has the largest halving time. So the first value will be 1 amp again. I'll give you a countdown and stop the timer when it gets to 0.5 amps. 3, 2, 1, start. That was a lot quicker, I'm sure you will agree. Please repeat this and you'll need at least 3 data points to get a good mean. I'm now going to select a middle value for the capacitance, and we're going to have a look at the effect of resistance next. So for a high value of resistance, our initial current is going to be 0.5 amps, so you will stop your timer at 0.25 amps. 3, 2, 1, now. And now with a smaller resistance, we'll be starting with 5 amps this time, so 2.50 amps please. 3, 2, 1, go. And I'm sure you'll agree that was a lot quicker. Please make sure that you are repeating these measurements and practicing collecting sets of data from which you can obtain a mean. After you've obtained your 4 means, I'd like you please to practice calculating absolute uncertainties and percentage uncertainties. Suggest some reasons for why these might be different. You should have found that the time to half is proportional to the resistance and proportional to the capacitance. So in this simulation, we showed that capacitance is proportional to area and capacitance is inversely proportional to the distance between the plates. In this simulation, we had a look at the effect of the dielectric, and we saw that the dielectric reduced the electric field. The electric field is voltage divided by distance. If we are reducing the electric field strength, then we are also reducing the voltage. We know from previously that the capacitance is the charge per unit volt. Therefore, if the voltage is going down, that's causing the capacitance to increase. In these simulations, we had a look at the movement of charge in series and parallel circuits. We looked at how in series circuits, the charge is passed from one capacitor to the next, but in parallel circuits, these capacitors work independently. And in this simulation, we had a look at the relationship between the time to half and resistance, and also capacitance. When a capacitor is charging or discharging, the charge stored on the plates, the current flowing through the wires, and the voltage across the plates, these are all changing all the time. In fact, the rate of change depends on the value at any moment in time. For example, the charge that is currently stored on this plate will impact the rate at which charge can be added to that plate. As soon as more charge is added, it will impact the rate at which charge can be added in the next second, and the next, and the next. We can say for these 3 variables that the instantaneous rate of change that is, the rate of change at any moment in time, depends on the instantaneous values of these variables. We have a changing rate of change. And this is not something that's been addressed at A-level physics before. Fortunately, there is an equation that can help. If you graph these values of y and x, then you get a graph where the instantaneous rate of change equals its instantaneous value. So we have our x and our y values, and this line is y equals e to the x. E is a number. It has a value approximately 2.71828, but it continues infinitely, in the same way that pi does. Pi is special because it helps us to understand circles, And E is special because it helps us to understand rates of change that are changing. This graph is special because at y equals 1, the gradient is equal to 1. At y equals 2, the gradient is equal to 2. And at y equals 4, the gradient is equal to 4. This equation allows us to connect instantaneous values with the rate of change at that moment. If we want to understand the way that current is changing, then we can use y equals e to the power of x to help us do this. We can connect our new value for current by multiplying the old value for current by a value or a percentage. For example, if I want to know the current, I take the initial value, which might be 5 amps, and I multiply it by a percentage. For example, 75%. So my new value would be 75% of the old value. And the way that we calculate this value is by using e to the power x. The variable in the power allows us to tailor the rate of change for the specific circumstances that we have. For example, this will depend on the circuit setup, and it will depend on the amount of time that has passed. The time is simply a measurement, but the circuit consists of many different things. The value of the resistor, the value of the capacitor, and the capacitor depends upon the area of the plates, it depends on the dielectric, it depends on distance. And what we end up with is e to the power of time over resistance times by capacitance. We also make this a negative value. The negative helps us to understand that this is a decreasing rate, because when we have current and time passing, as you saw in the simulation, the current is going from a high value to a low value, and the negative helps us to understand the way that that is happening. Is it happening slowly and then quickly, or is it happening quickly and then slowly? The negative here tells us that it is this kind of behavior. When a capacitor is charging, the current is decreasing, the charge stored on the capacitor is increasing, and the voltage across it is also increasing. The graphs are going to look like this. For a discharging capacitor, again, current will be decreasing, the charge stored on it is decreasing, and the voltage across it is also decreasing. We will have a look at these graphs first, given that they are all the same shape, and this situation is slightly more complex. There is our expression for current. It will also be the same here, because it's the same pattern of behavior. Remember, this follows from y is e to the x, and the values that are in that power help us to understand the rate at which this is changing, and also the shape. So we can see that this is happening quickly and then slowly, quickly and then slowly, which is why we have the negative. It depends on the time, the resistance, and the capacitance. So for charge, the equation is the same, but with charge instead of current. Voltage, we also get the same equation. But these two are increasing. They are moving quickly and then slowly, quickly and then slowly. So we're still going to have the negative sign. And they also still depend upon time, resistance, and capacitance. So that will be identical. But they are mirroring this graph up here. In fact, if we place a mirror between, you can see that it is happening the opposite way. This one is dropping 50%. This one is gaining 50%. From here to here, it is dropping to 25% of its initial value, and here it is rising to 75% of its final value. So what we do is we need to take that percentage change and flip it by doing this. So 1 minus in both cases. There's a couple more things we can say about these graphs. If we recall that the x-axis is time, we know these to be true, and therefore the area under this graph and under this graph must be the charge. And the gradient of this graph and of that graph must be the current. In the last simulation, you were taking measurements of halving time. We started off with an initial current, and you timed how long it took for that value to halve. We know that this is the way to calculate the new current from the old, and therefore this must have a value of 0.5. If we solve for the power, we find that this is true, and therefore T over RC is 0.69, and therefore the time for halving must be 0.69 RC. This works for values for current, for charge, and also changing voltage.